We learn to recognize objects by shape and size. We say the Earth and the Moon are round because each shape is spherical. And we describe the size of a spherical object by its diameter. This scale model of the Moon has a diameter of 6 feet. It has the same shape as the Moon, but the Moon is much larger, with a diameter greater than 2,000 miles. All around us, we recognize objects that have virtually the same shape, but come in different sizes. For example, families of seashells come in different sizes, but have very nearly the same shape. The little pyramid on the right is dwarfed by the giant pyramid of Cheops, but it has the same shape. When they design new automobiles, engineers build scale models to check airflow and measure wind resistance. And some people are fascinated by model airplanes. They're used as toys and as collector's items. This scale model of the Tacoma Narrows Bridge was built to learn why the full-size bridge collapsed. In the classic science fiction thriller Manhole Monsters, invaders from outer space have enlarged small garden creatures more than 80 times their ordinary size. We'll see how to defeat such monsters with a little mathematics. Questions about shape and size can be answered using geometry. Early civilizations used geometry not to study giant insects, but to build magnificent temples. The Greek mathematician Thales and the Pythagoreans studied geometric figures that had the same shape. Eudoxus invented the theory of ratios, and Euclid put it all together in books 5 and 6 of his Elements. Today, we say that objects with the same shape are similar, from the Latin word similis, which means alike. Similarity is basic to all measurement. Every manufactured object, from a microchip to an aircraft, starts with a scale drawing or model which reproduces the same shape at a smaller or larger size. A globe is supposed to be a scale model of the Earth, but in this globe, vertical distances have been exaggerated about 12 times to reveal features such as mountain ranges. If the Earth was similar to this globe, Mount Everest would rise 348,000 feet above sea level, instead of its true elevation of 29,002 feet. In a true scale model this size, the surface would be quite smooth, with Mount Everest only 1/16 of an inch high. Maps of flat surfaces reduce all distances in the same ratio, but don't change shapes. In this street map of Washington, D.C., 1 inch represents 4/10 of a mile. We also use similarity when we test a model in a wind tunnel to learn how the full-size craft will respond under the same conditions.